Hey everybody, this video is obviously for section 1.6 and we're going to review from Algebra 1 how we deal with absolute value equations and absolute value inequalities. So we're going to talk about the solutions to an equation that involves absolute value or an inequality that involves absolute value, and see what kind of dynamics the whole absolute value involvement means. So start with a question. Can you list the solutions to something really basic, like the absolute value of x equals 5? So it's like, in other words, the absolute value of what numbers would just equal 5. And, you know, so you could say x could be equal to 5 because the absolute value of 5 equals 5. But guess what? There's another answer, which you probably have already thought of by now. The absolute value of what other number would also equal 5? And of course, that would be -5. And that's just because of the nature of absolute value. It's how we define absolute value. There'd be two answers. First answer 5, other answer -5. Moving on to this, making it a little more complicated. Now it's not just the absolute value of x, it's the absolute value of 2x minus 4. And the whole equation says the absolute value of 2x minus 4 equals 12. What would be the solutions to that? And in order to, talk about that, in order for this equation to be true, you could say that the whole quantity of 2x minus 4 could be like positive 12 in disguise, or it could also be a -12 in disguise. This entire 2x minus 4, if that entire 2x minus 4 was equal to 12, we'd be in business. Or if that entire 2x minus 4 was equal to -12, we'd be in business. It would all work out. And so you could literally write that. 2x minus 4 could equal positive 12, or the 2x minus 4 could equal -12. And then you can kind of go off of that and eventually figure out what x would have to equal to satisfy this case. And then you could also figure out what x would need to be in order to satisfy the other case, the negative case. So I guess some textbooks and teachers might use that word a lot, two cases. You have the positive 12 case and you have the -12 case. Anyway, solving this real simple, like you've done thousands of times. If we add 4 to the other side, to get 2x all by itself, get 16. And then if we divide both sides by 2, to finish solving for x, we get positive 8 over here. If we added 4 to both sides, we'd get there. And then dividing both sides by 2, I think we'd get -4. So the two answers, the two solutions to this equation would be positive 8 or -4. And that's essentially a pretty good format, like a pretty good overall outline strategy for solving equations with absolute value. Kind of break it up into two cases. But you're not going to do that until you isolate the absolute value. So, like this equation, you couldn't just think about the two cases right now. Like, you can't look at that and go like, oh, there's a positive 10 case and a -10 case. No. In order to jump to that point of the solving, you got to have the absolute value isolated. So actually, the first thing we're going to do here is undo that minus 5, and essentially, long story short here, we're going to be getting the whole absolute value of 4x minus 1 part alone on the left side. And this is the first step, and so and then the next thing we're going to do is divide both sides by 3. Okay, we're not going to distribute the 3. And so that leaves the absolute value of 4x minus 1 all by itself, and the other side would be 5. See, now we can look at it and talk about the two separate cases, where the 4x minus 1 could equal positive 5, or the 4x minus 1 could equal negative 5. So the step-by-step strategy is going to be to basically make sure the absolute value part is isolated and then split up into two cases, where the first case is your positive case and the second case is, the negative case. And now you just, solve each for x, and so I believe this is going to be 1.5, 3 over 2. And over here, it's going to be negative 4, and so x equals negative 1. And so we have two answers, seemingly, 1.5 or negative 1. So if we plugged in negative 1, let's just say, 4 times negative 1 is negative 4, minus 1, negative 5, and then we take the absolute value of that, so we get positive 5, times 3 is 15. Yeah, so this checks out. This checks out. What if we plugged in 1.5? 4 times 1.5 should be 6. 6 minus 1 is 5. 3 times 5. Yep. So they both check out. So there really is two answers. And again, that's the overall strategy. And same thing here. I see the absolute value isolated. And so now we can break it up into two cases where the 3x plus 2 would equal like positive overall 4x plus 5. But there's also the other case where 3x plus 2 could equal the negative of that entire right side. And why don't I emphasize that by first writing it in parentheses with a negative out in front. And so that basically ultimately will mean negative 4x minus 5. And now we can kind of solve both of these separately, just like before. And I'm going to subtract 3x from both sides so that it's a positive x over on the right. And then I'm going to subtract 5 from both sides and essentially get x equals negative 3 over here. I'm going to add 4x to both sides first, and that'll just leave a negative 5 on the right. Now I'm going to subtract 2 from both sides, start to get x all by itself, and so then of course divide both sides by 7. So x equals negative 3 or x equals negative 1. But try to get in the habit of checking both answers, especially in these situations where you have a variable over here that is involved in the whole like positive case or negative case. And so if we plug in negative 3 back in here, I'm just going to do this verbally, So 3 times negative 3 is negative 9, even though writing this out would be a little bit smarter, but 3 times negative 3 is negative 9. Negative 9 plus 2 is negative 7. And then the absolute value makes this whole side 7. Right? So we have a 7 over here. 4 times negative 3 is negative 12. Plus 5 is negative 7. So positive 7 does not equal. So this is what we call an extraneous solution. Especially if you consider the root word extra. Okay? It's an extra, really non-solution. Okay? That was created by the strategy of the algebra that we were doing in order to solve this. It's not actually a solution, and again, that can happen in this sort of situation. Not so much here, not here, right? Not here, but when you have another variable over here, like this can totally happen. Now plugging in negative 1 to see if this is a solution. 3 times negative 1 is negative 3, plus 2 is negative 1. And so when you take the absolute value of that negative 1, you get positive 1. So then 4 times negative 1 is negative 4, plus 5 is positive 1. So this does check out. So actually, at the end of the day, there's not two answers to this absolute value equation, just one, and it's x equals negative 1. This next example, are we ready to do the two cases yet? No, because we want the absolute value of 7x minus 5 totally isolated, so we're going to, since this is 2 times the absolute value, we're going to divide both sides by 2 to get the absolute value of 7x minus 5 all by itself. And now, normally we would pull the trigger on the two cases, right? But if you've noticed, it's always been the positive case, and then the second case is the negative case. This 8 is already negative, or the negative 8 is already negative. So if you're thinking this might be weird looking, like something doesn't feel right, then you're right. Think about this. The absolute value of what could equal negative 8? Like, what could 7x minus 5 be equal to for, like, what if it was just the absolute value of x equals negative 8? Like, you tell me, the absolute value of what number would equal negative 8? Nothing, So when this number is already negative, we have kind of a unique, not unique I guess, but very special situation. And there won't be any solution. So you got to learn to have a good eye when it comes to stuff like this. And if this number is already negative, there can't be any solutions. Because the absolute value of something can never be negative. It's just the way absolute value is. Like, I know it works. I know based on what we've done. I mean, this makes sense. The absolute value of something would equal 12. This is how absolute value is. That's how we define it. So this 2x minus 4 could equal positive 12, or it could equal negative 12. But in this situation, it just doesn't work. And there's no solution. Now let's move on to inequalities, where we have less thans and greater thans and so on. Let's start with the less thans. Less than, or equal to, because we're also going to sort of draw a line, so to speak, between like the whole less than stuff and greater than. It's going to be like sort of two different scenarios. So can you list some solutions to the absolute value of something, the absolute value of x, is less than 5? What kinds of numbers would make that true? Well, obviously, 1, 2, 3, 4, okay? 0. Any other kinds of numbers, other than like, 2.5, 3.5. What other numbers what other types of numbers could you plug in for x where like the absolute value of it is still less than 5? Are we talking about like -1? Couldn't we throw -1 in there? -2, -3, -4, stuff like that. What about 5? Would 5 make that true? No, it wouldn't. Would 6? No, of course not. Would -6? Is the absolute value of -6 less than 5? No, it isn't. So it's like we're basically talking about anything in between -5 and 5. And of course, not including -5 and 5. So I think you should know what the graph of that would look like. But if you were to break this up into two cases, because we're also going to talk about the whole two-case thing here. And so if we were going to break this up into two different cases, you could say that x is less than 5, but at the same time, x is greater than -5. And wouldn't this need to be an AND situation? I mean, wouldn't that just fit the whole scenario? X is less than 5 and x is greater than -5. And so notice the original absolute value inequality, and then case number 1, and then the changes that were made in case number 2, where you just flipped it to a greater than and made the 5 negative. Don't you think that is going to be like a pretty good format for anything, even as we move into more complicated inequalities like this? The absolute value of 2x minus 1 is less than or equal to 5. That's how we're going to do the whole two-case thing. And like our good friend Mr. Burchanowski says, two absolute value lines, like that's the whole notation for absolute value. Two vertical lines, well, guess what? Two cases, like we've been saying. And so just like we looked at here, it's going to inevitably be that 2x minus 1 can be less than or equal to 5, but at the same time, 2x minus 1 needs to be greater than or equal to -5. And the word that fits the situation here is AND. All right? And so we're dropping the absolute value, notice, when we split this up into the two cases. And so here, now we're just going to solve these separately. Add 1 to both sides, and we get 6. And then divide both sides by 2, and get x is less than or equal to 3. Over here, we add 1 to the other side, and we get -4. And then when we divide both sides by 2, we get -2, and overall x is greater than or equal to -2. So we have our final sort of solution as being, anything less than or equal to 3 and greater than or equal to -2. And as you should know from Algebra 1 in our previous section 1-5, this is going to mean like one of those in-between type graphs. Anything in between and including, because of the whole or equal to symbols, anything in between and including -2 and 3. And normally we're going to have to graph these, and that's what the graph would look like. Everything in between -2 and 3, and including those endpoints. So let's do another less than or equal to example, following the same format. Sorry. So, and again, like it doesn't apply here. It doesn't apply here, but I should probably say this at least once. Well, I should probably say this already. I shouldn't wait any longer to say this. Okay. You're not going to do the whole two-case split up thing until you make sure the absolute value has been isolated. Just like with the equations. You're not going to split up into two cases until you've isolated the absolute value. And like I said, a few seconds ago, it doesn't apply here. The absolute value is already isolated. So we can do the whole two cases thing, where in the first case, the 3x minus 4 would be less than or equal to positive 8, just like as is pretty much. But in the other case, it's going to be greater than or equal to negative 8. You flip the symbol and make the 8 negative. And again, the word that fits here is and. It just fits, with the whole original symbol of being less than or equal to. And now you're just going to solve both of these separately like you've done 1,000 times. No need to reteach you that. And these directions specifically say to graph the solutions. And just like I said, especially when the word is and, it's going to be greater than or equal to negative 4/3 and less than or equal to 4. That's obviously going to look like this, where the graph is in between. The graphs collide. And you just take the overlap, the whole and vibe, and this is what the final graph would sort of look like. Okay? Let's see what happens with greater than. If the original symbol is greater than, how does the whole absolute value thing work? So can you list some solutions to this? The absolute value of what would be greater than 3? Well, now we're talking 4, 5, 6, right? 6.5, 6 million. But what else? Would 3 be a solution? Not here. 2, 1s, no. But what else would be, when you take the absolute value of it, it's bigger than 3. Aren't we also talking negative 4, negative 5, negative 6, whatever? In other words, and again, let's cut to the chase. If we're talking about how to describe this, like all the answers, not just these separate integers, like would 3.5 work? Yeah, 3.1, negative 3.0001. Again, describing all the answers with this whole two cases thing. Wouldn't it be, you could be x is greater than 3, or you could be less than negative 3. And the word that fits here is an or. You could be greater than 3 or less than negative 3. It's not like you have to be both at the same time. It's not complicated to, or it's not hard to understand that the word and doesn't fit here, but the word or does. X is greater than 3 or x is less than negative 3. And that's your two cases with the word or. And that's how we're going to approach all this stuff with a greater than or a greater than or equal to. Anything greater than, that's how we split up into two cases, where here the 2x minus 4 could be greater than or equal to positive 2, or the 2x minus 4 could be less than or equal to, and then you make the 2 negative. You flip the symbol and you make the 2 negative in the second case. And now you can just solve each one separately. Over here we add 4 to the other side, and I believe we get 2. And then we divide both sides by 2, and we get 1. And so describing all the solutions to this, you could be greater than or equal to 3 or less than or equal to 1. And so doing another example like this, with a graph included at the end, I mean, just think about what that graph would look like. Probably going to be a typical OR graph. Now, do we need to do any isolating of the absolute value? No, it's already by itself on the one side. So we can go right to the two cases where the 2x minus 4, again, we're dropping the absolute value for the two cases. That 2x minus 4 would be greater than or equal to 2, or 2x minus 4 is going to be less than or equal to negative 2. Why do I feel like greater than or equal to 2? Why is this the exact same example? I just realized that. Is it the exact same example? How did that happen? Oh well, it's the same. It would have been the same old thing anyway. So the final answer, greater than or equal to 3. Well, let's just play this out again. So 2x equals 6. This is greater than or equal to 3. 2x is less than or equal to 2. X is less than or equal to 1. I mean, we can at least include the final graph here. And the fact that the word is an OR, that usually tells the story of the graph, It's 1, it's 3, so we could be less than or equal to 1, or greater than or equal to 3. And no surprise that the graphs are going away from each other. Okay? And that's essentially it, So to kind of summarize, right? The summary I'm not going to write this down on the last page, but you can feel free to paraphrase and summarize in your own words. But to summarize this, if you had an equation, okay, the first thing you do is you make sure the absolute value is isolated. Make sure the absolute value is isolated. Then you split up into two cases, where the first case is your positive case, and your second case is your negative case. And then you just solve each case. And be sure to check to see if you have any extraneous solutions. With inequalities, whether it's a less than or equal to, greater than or equal to, if it's any kind of inequality, once again, you make sure you have the absolute value part isolated, and then you split up into two cases, where your first case is just sort of like as is, and in your second case, you flip the symbol and make the number on the right negative, as you've seen in these examples. And the word that fits is if it's more than, it's or, and if it's a less than, the word that fits is and. So, less than and, more than or. And there's different ways to say that, like less than and, greater than or, but that's basically the summary, And before I end this little video, I just want to point out that this ended up being, it's more like this, right? Once you isolate, you can only really tell after you isolate the absolute value. So it's really looking at this, not that. But this was a pretty strange, specialized example for absolute value equations where there ended up being no solution. What could possibly be weird with inequalities. You know what I mean? I'll just give you a couple simple examples. Like, what if you had something like that? The absolute value of what is greater than negative 3? Wouldn't that be always true? Like, wouldn't that be any real number you plug in for x? Wouldn't that be the absolute value of it would be greater than negative 3? So this would have like all real numbers as solutions. But if you did something like this, absolute value of x is less than, say, negative 3, now the final solution to this would be that there like is no solutions. So this would be all real numbers, and this would be no solution whatsoever. And that's it.